The examiner will expect you to know some of the tricks to working with very small or very large quantities. In this lesson, the tricks we'll consider are estimations, standard form, orders of magnitude, and using prefixes. Estimates are not the same as guessing. An estimate can be used when we have an idea of the approximate size, or even just the order of magnitude of a quantity, but where an accurate figure is inconvenient or even impossible to obtain. If we wanted to count the number of open stomata cells on a particular leaf, or the number of spiders in a field, it could take an unreasonable amount of time to count them one by one. And by the time you get to the last area, things may have changed. Some of the spiders could have walked off, more could have entered the field, others could have died or been born. You can't freeze time, but you can get a useful approximation of the real figure. If we choose an area that's not too big to work with, then we can count how many are in that area. We can then scale that count up according to how many equivalent areas there are. We won't have the true figure, but our estimate provides useful information. Estimates are also a really useful common sense check that we can apply when we're trying to work out a calculation. If we round figures so that they're easy to work with, then we can get a figure that'll be close to the real answer. And we can then use that figure to check if our arithmetic has been worked out correctly. Use estimations to decide which animal is the fastest animal runner. A hedgehog that takes 27 seconds to run 175 meters across a field, or a field mouse that takes 10 seconds to run 36 meters to its burrow. There are two equally good ways to use estimation for this. In the first, we can see that the time for the hedgehog run is approximately 3 times as long as the mouse run. But 3 times 36 is obviously a lot less than 175. So the hedgehog must be the quickest. The other way is a bit longer. We round each number up or down and then do the calculations and compare. For the hedgehog, we could round this up to 30 seconds to go 200 meters. So we get 400 meters in a minute. For the field mouse, we could round 36 to 40 and multiply this by 6 to get the distance covered in a minute. 6 times 40 is 240, which is a lot less than 400 meters for the hedgehog. Now, if multiplying 6 by 40 is difficult, you could split it down. 6 is 5 plus 1, so if you multiply by 5, then add 1. Multiplying by 5 is easy. You just multiply by 10 and half it. So doing it this way, 40 times 10 is 400. Half of this is 200. Add another one lot of 40 and you get 240. So estimates also help us to check the arithmetic or logic of a solution as we work through a problem. If we counted the number of spiders in our quadrat in 3 areas to get an average value of 4.99 per meter square, and the field is 95 square meters, 4.99 times by 95 could be approximated to 5 times 100, which is 500 spiders. If our calculation turns out to be 47.5 spiders, or 4,750 spiders, then we know there's a mistake somewhere. Very small or very large numbers can be awkward to work with. It can be difficult to understand what they represent or how they compare to each other. For instance, Mount Everest is 8,848 meters high. The bar-headed goose, which migrates over the top of the mountain, measures around 0.75 meters in length. It's difficult to relate these figures to each other, but using standard form or orders of magnitude makes them easier to understand. Standard form makes it easier to work with very large or very small numbers. 8,848 meters is 8.848 times 10 to the third meters in standard form. 0.75 meters is 7.5 times 10 to the minus 1 meters in standard form. This may not seem easier, but when you get used to using it, it really is. Now there are two aspects to standard form: the number or the digit and the exponent or index. Standard form is about the number of powers of 10. The exponent or index written above the number 10 shows the extent to which the number or the digits are multiplied by 10. To get the figure in decimal form, the decimal point shifts place by the number of the exponent. If the exponent is negative, that means the number is small and you need to divide by 10 that many times, and the decimal point moves to the right. If the exponent is positive, then the number is large and you'd need to multiply by 10 that many times, and the decimal point would move to the left. If necessary, to keep things in standard form, the index can be 0, showing that the number is multiplied or divided by 10 0 number of times. So a value of 5 is written as 5 times 10 to the power 0, and a value of 50 is written as 5 times 10 to the power 1. To keep things consistent for everyone, the digit part of the standard form is always between 1 and 10. So it's either 1, 2, 3, 4, 5, 6, 7, 8 or 9. It's never 0 and it's never 10. So 4,567.89 will be written as 4.56789 times 10 to the power 3. To two significant figures, this would be 4.6 times 10 to the power 3. So try writing the following numbers in standard form. And try writing the following as a decimal value. Another useful way of allowing us to compare very small or very large values is to consider their order of magnitude. An order of magnitude is a multiplication or division by 10. It's like comparing the index number of a value written in standard form. The digit part of the standard form is largely ignored as it's of less significance than the index. If something is an order of magnitude larger than something else, it's around 10 times bigger. If it's around 100 times bigger, then it is 2 orders of magnitude bigger. Now we only compare things by order of magnitude when there's a large difference between them. If the larger value divided by the smaller value is less than 10, then they are of the same order of magnitude. So 75 and 9 have the same order of magnitude, but 75 and 0.9 have different orders of magnitude. So using orders of magnitude, how many times heavier is a blue whale of 170,000 kilograms than a human of 75 kilograms? An easy way to do this is to convert both numbers into standard form and then compare their index numbers. So 170,000 kilograms is 1.7 times 10 to the fifth, and 75 kilograms is 7.5 times 10 to the power 1. The difference between the index numbers is 4, so there are 4 orders of magnitude of difference between their weights. See if you can work out how many orders of magnitude different their lengths are. The blue whale is around 25 meters in length. The human is around 1.7 meters in length. So that's 2.5 times 10 to the power 1 and 1.7 times 10 to the power 0. There's 1 order of magnitude difference between their lengths. Using standard form is very useful when performing calculations. But when discussing relative sizes, it's more convenient to use prefixes to indicate the index number of the value in standard form. If the index number of a value written in standard form is 3, it's 10 times 10 times 10, or 1,000 times bigger. In this case, we'd use the prefix kilo. So 1 kilogram is 1,000 grams. If the index number of a value is -2, then it's 100 times smaller. We then use the prefix centi. So there are 100 centimeters in a meter. If the index number is -3, then it's 1,000 times smaller, and we use the prefix milli. There are 1,000 millimeters in a meter. If the index number of a value is -6, then the value is 1,000,000 times smaller, and we use the prefix micro with the symbol mu. There are 1,000,000 micrometers in a meter. And if the index number of a value is -9, then it's 1,000 million times smaller, and we'd use the prefix nano with the prefix n. There are 1,000 million nanometers in a meter. So convert the size of these objects into standard form to compare how many orders of magnitude difference there are in their length. It's crucial to consider units when you're doing calculations. All the values for a particular measurement need to be in the same units. If you're calculating magnification, for instance, and the length of the real object is in micrometers, but the size of the actual object is in centimeters, you need to convert them both to the same units before applying the formula to find magnification. Now, the best way to convert units is to consider the difference in their order of magnitude, their index, if you like. If one unit has an index of -2, meaning it is in hundredths, and the other unit has an index of -6, meaning that it's in millionths, then there's a difference of 4 orders of magnitude. The larger unit is 10,000 times bigger than the smaller unit. So, to convert micrometer measurements, which are 10 to the minus 6, to centimeter measurements, which are 10 to the minus 2, you need to divide by 10,000, because there are 10,000 micrometers in every centimeter. The micrometer is much smaller, so you need more of them. Okay, now consider the order of magnitude of the following values and then use that to work out the conversion.